So thank you. I'd like to begin by thanking the organizers for inviting me to be here. It's been a wonderful program. I've really enjoyed my last 2 weeks here. Okay. So the title of my talk is.
Can you turn your microphone?
Oh, microphone. Hello? Hello? Good? Okay. Okay. So the title of my talk is Holographic Entanglement Entropy and Higher Spin Gravity. And this is some work that I did in collaboration with Martin Emin and Alejandra Castro. Alejandra is there. And so I'm going to begin, so the title of this talk sounds kind of like a bunch of two things that aren't obviously correlated with each other. So I want to begin by just motivating why I think this is actually an interesting thing to study. All right. So let's go on. So I'm going to begin in this sort of vague manner. What is geometry? So this is very vague. But what's sort of fun about it is that in the era of ADS-CFT, it's a vague question with many answers. There's many ways to think about this now. So of course, geometry is the things that are curved, manifolds, tensors, etc. But also, under certain circumstances, it's something different. Under certain circumstances, we know that gravitational theories, so geometry on ADS, is dual to CFT in one lower dimension. And thus, sometimes geometry is an emergent phenomenon. It comes from microscopic degrees of freedom, quarks and gluons, they interacting with each other in ways that give rise to a totally different description. And this is something that we're all familiar with from ADS-CFT, and it's, again, like I said, very vague. So it's of interest to try to make these notions more precise. And people have been trying to do this in lots of different ways. And there's one way which I think is very promising. So what is that way? There is some clues about how we might want to do this. So everyone here knows what entanglement entropy is, but just to set notation for what's going to come later, let me just review. So forget about holography and gravity for a second, and think about some general quantum field theory in some state, and a spatial region A in that state. So you can construct a reduced density matrix by tracing out everything that's not in A. There's a number that you can associate with this region A, and that number is the entanglement entropy. So just the von Neumann entropy of the reduced density matrix. Now, let me again just remind everyone how the entanglement entropy behaves in pure states in a quantum field theory. So in a pure state, what this number S measures is the quantum entanglement between region A and stuff outside region A. It's complement. So in a quantum field theory, the dominant part of this answer actually comes from short-range correlations between that sort of live at the boundary. There's lots of short-range correlations between things just inside A and just outside A. And thus the answer scales like the area of the boundary of A. So this is the area law. And this area law sort of breaks down in a very nice way in two-dimensional conformal field theory. So in two-dimensional conformal field theory, the area, the boundary of a region A is just an interval, and the boundary is 2 points. And so the answer, though, isn't just constant. Nonetheless, it's a log. It's a log in the where L is the length of the interval. And this is a classic result that has been computed by lots of famous people. So this is the standard result from CFT. Now, this is what you get in a pure state. If you're in a mixed state, on the other hand, the entanglement entropy measures something different. If you make your region big enough, it basically just measures the ordinary entropy contained in A. So in a mixed state, there's some entropy density, probably, if you have a translationally invariant mixed state, there's some entropy density. And if you make the region A big, then what this entanglement entropy does is it just counts the ordinary entropy contained in A. So you get something like this, if this S naught is the entropy density, and VA is the volume of this region A. So it's extensive in the size of the system now. So again, you can get an exact result in 2D CFT at finite temperature. The reason you can do this is because the finite temperature 2D CFT on a line is the cylinder is conformal to the plane, and basically anything you can do on the plane, you should then be able to do at finite temperature. And so you can compute the entanglement entropy at finite temperature, and you get some answer like this. The precise formula is not that important. What you should notice is that if you take L very, very large, the sinh becomes an exponential, the log is the exponential, and you get something which scales linearly in the size of the interval, which is just, again, precisely this phenomenon right here. Okay, so these are all very standard results. Now, if we're instead thinking about holography, then everyone knows there's a sort of very nice way to compute entanglement entropy if your CFT has a normal gravity dual. So by normal, I mean, say, dual to Einstein gravity, maybe some benign higher derivative corrections, maybe some other fields. Under those circumstances, there's a nice way to compute entanglement entropy, which was first proposed by Ryu and Takinagi a number of years ago. The answer is, what you do is, in the bulk, you find a minimal surface which ends on the boundary, at the boundary of A. Okay? The area of that bulk minimal surface is the entanglement entropy. And there's lots of talks about this. I'm just going to give you two examples. Just to, again, to orient ourselves. In a 2D CFT with an ADS3 bulk, the minimal surface is not a surface, just a geodesic, a spatial geodesic hanging into the bulk. And for pure ADS3, you find this log behavior that you expect from the vacuum of a 2D CFT. The reason it's a log is because as you make it larger, the bottom of this sort of dips deeper inside, and ADS is smaller in the inside of ADS, and thus it doesn't grow as quickly as the interval. It grows only as the log of the interval. For a thermal state, it's a little different. Here, this thing can't dip down. It merely hangs on the horizon like this. And so you end up just counting the length of the horizon. That's what this thing counts. And the prefactor now must agree, because this is basically just counting the section of the horizon that you're capturing. So in 2D, you can precisely calculate everything in the bulk by computing lengths of geodesics. Everything agrees exactly with that from the CFT, as it must. Okay. Now, that's fine. So here are some thoughts about this formula that I still find remarkable. The Ryu-Takinagi formula provides a direct connection between two things that are sort of very primitive on either side of the duality. On one side, you have entanglement, which is a really basic notion. Any quantum mechanical system has entanglement. And somehow that entanglement is directly related to a very basic geometric idea, minimal surfaces. It did not need to be so simple. It's nice that it's so simple. I'm still very happy about this. And you really get the feeling that if you understand the full entanglement pattern in the field theory, you can sort of build your geometry from the entanglement pattern. If you know how everything is entangled, you know every possible surface. In some sense, you know the geometry. And various people have been trying to implement this. There's lots of people, like Ramsdonk, Swingle, collaborators, who are trying to do this and make this more precise. And there are various ways to do this. So what I'd like to do is try to extend these ideas to a situation where the notion of geometry, so the left-hand side of this equality, is less clear. Okay? So I have something particular in mind. So higher spin gravity. Okay. What is higher spin gravity? There's been a great deal of interest in this recently. So here are a list of people who wrote some of the foundational papers, but there's been a lot of work on it, and so I can't try to list everyone who's worked on this. But there's been a lot of interest in it. And what these theories of gravity are is they contain massless higher spin fields in the bulk, in addition to the graviton. So if we're working in a four-dimensional bulk, you in fact have an infinite tower of massless higher spin fields, organized in a specific and complicated way. So just as string theory in the bulk is thought to be dual to gauge theory in the boundary, higher spin theories in the bulk are thought to be dual to vector-like field theories in the boundary. Okay? And for example, a certain theory in the bulk, the Vasiliev theory in ADS4, is thought to be dual to the ON vector model in 3 dimensions. So in 4 dimensions, these theories are very complicated, because you always get an infinite tower of spins. However, if you're working in 3 bulk dimensions, life is a lot easier, because you can actually stop at any spin you want. You can fix some n and get all spins up to that n. So this will make life a lot easier, and we're going to work in that for what follows. But now, the thing that I find really fascinating about these theories is that they have a very, very large gauge redundancy. They have a complicated gauge structure in the bulk. And these gauge symmetries actually act very non-trivially on the metric. In particular, they don't leave the geometry invariant. Okay, they act in a way that's unfamiliar on the geometry. So what I mean by that is, for example, in 3D, there are black hole solutions to higher spin gravity. You can make a black hole solution. People have done this. And then you can act on it with a gauge transformation. And the gauge transformation will remove the horizon of the black hole. Okay, it will change the causal structure of the black hole. And after the transformation, this guy will look like a traversable wormhole. Okay? However, these are describing the exact same CFT state, so they must be describing the exact same physics, but somehow our usual notion of geometry, or a way to organize our thinking about that physics, doesn't work under this setting. So our usual notion of geometry is no longer gauge invariant, and we need some sort of better way to think about geometry in this higher spin setting. So this is the question, this is the problem. And so, given what I just said, you might think there's sort of a natural way to try to generalize the notion of geometry. And that's to take this correspondence between entanglement entropy and geometry seriously. So these theories are still dual to CFTs, and so they have a well-defined notion of entanglement. And so we can still ask, what is the bulk object that computes entanglement entropy in higher spin theories of gravity? Geodesics won't work. Okay, they will not work. It's not even a gauge invariant notion, the notion of a geodesic. But you might think there should be some object which does this. And if we can answer this, I think it'll be fun, because it will help us think about the question, what is geometry in higher spin gravity? What is the more general idea that entanglement is telling us to take seriously? And so this is the question that I'm going to try to answer during this talk. So I just finished number 1, motivation. So actually, are there any questions at this point before I go on? Yes?
Are there no invariants under this light gauge transformation?
Good. In 3D, there's very natural invariants, which I'm going to be using a lot. In 4D, it's a much more complicated question, and I'm not exactly sure, to be honest with you. But in 3D, there's a simple answer, and I'll be using that. You'll see it in a second. Yeah. Good. Great question. Okay,
so
good.
The length of geodesic is not invariant under this.
That's right. Yeah, that's right. Exactly. Length of geodesic is not invariant under this.
Are you in a 3D bulk or?
I'm in a 3D bulk. So I haven't specialized yet. I will in a second, but I will be in a 3D bulk for the rest of this talk. Yeah. And that's a 2D CFT. Okay. So what I'm going to do is I finished motivation, hopefully. What I'm going to do first is I'm going to talk about how to formulate normal spin 2 Einstein gravity in a Chern-Simons language, and explain how to compute entanglement entropy in that language. This is not trivial, actually. This involves a fair amount of work. Once you do that, it's clear how to generalize it to higher spin theories of gravity, and that's point 3. And I'll conclude with a brief discussion. Okay. So first, to explain how to think about higher spin gravity, I'm first going to explain how to think about normal ADS3 Einstein gravity in the Chern-Simons formulation. So it's a fact that pure gravity in 3D has no propagating degrees of freedom, and so you can write it as a Chern-Simons theory. So this is a well-known fact going back to these people from the late 80s. And so the action of pure 3D gravity looks like this. I have 2 gauge fields, A and A bar. A and A bar are each in the gauge group SL2, and I claim that the Einstein action is equivalent to this double Chern-Simons action. Okay, they're exactly the same thing. And so this is a convenient way to write the action for pure 3D gravity. Now, the reason why this will be useful for us for higher spin gravity is that you see this 2 here. If you replace that 2 with an n, you actually get a theory of higher spin gravity. So I'll explain that in a while. But for now, just keep this in mind, that you can easily generalize this Chern-Simons description to higher spin theories of gravity. And if you want to make contact with more familiar ways of writing this action, you can recover the Vielbein, the spin connection, and the metric from these gauge fields in the following way. The Vielbein is the difference between of A and A bar. The spin connection is the sum. And you construct the metric from the Vielbein in the ordinary manner. So everything you know about 3D gravity can be rewritten in terms of these variables. And a lot of things just look a lot nicer. And a lot of things don't, as we'll see. Okay, so in 3D gravity, we have no propagating degrees of freedom, but we do have things. We can have black holes. So let me just tell everyone what a BTZ...
The level of the Chern-Simons?
Good. The level of Chern-Simons theory is K, and it's related to central charge. C equals to some number times K. I've forgotten what normalization I have for this action here, but it's some constant times K.
ADS gravity?
So you can do this for flat gravity as well. The gauge group then is not SL2 times SL2, but ISO 2, 1. So just the Poincare group. You can see that what you want basically is you want the isometry group of your spacetime to be the gauge group of this gauge field. Yeah, you can do it for flat space and de Sitter too. Okay. So you don't have any propagating degrees of freedom, but you do have things. You have black holes in this theory. So let me remind everyone what the BTZ black hole looks like in the Chern-Simons language. So I want to solve the equations of motion. This is really easy because the Chern-Simons equations of motion just tell you the connections are all flat. Okay. So what that means is a black hole is some sort of defect. It's like a point sitting in the center of ADS, which has a non-trivial holonomy for the gauge fields around it. It's kind of like a flux tube sitting in space-time. And so it's characterized by having a phi cycle. If I move around this black hole, so this is the black hole right here. If I move around it, the phi cycle is non-contractible, but the Euclidean time cycle is contractible. So that's how to think about a black hole in the Chern-Simons language. And so the information about the black hole is stored in the holonomies of the gauge field around the phi cycle. So there's a holonomy of this gauge field. it's some SL2 matrix. That SL2 matrix carries the data of the black hole. For example, the mass, the angular momentum, etc. So one thing that you can sort of see kind of immediately from this is that the black hole looks like a point-like defect here, and thus the existence of the horizon is not a tremendously obvious concept in the Chern-Simons formulation, at least when I think about it. To see this horizon, I think you actually have to compute the metric and look at it to see it, which is not a natural thing to do in the Chern-Simons language. So already this Chern-Simons language kind of obscures some geometric aspects of the theory. Okay.
Exercise
Yep.
notion when you go to a flat space time and you have a conical singularity.
Yeah.
I guess you have the same holonomy structure describing it.
Yeah, exactly. You can even think about conical singularities within this exact framework. You can precisely characterize the different singularity structure. That's right.
And then the conical singularity is a more empty object than the black hole, and I guess that's really
More empty. Good.
it's no matter.
I think it might be more. That's a good question. Is it more empty? I'm not sure how to characterize more empty, but you can certainly think about it mathematically in this language. Yeah, that's right.
What is the phi?
Sorry.
The phi.
Good. A phi is just the phi component of this gauge field here. Yeah. So this is just the holonomy of A around this cycle. That's all. Good.
Yeah, the mass should be different for conical singularity.
Yeah. That's right. That's right. The mass is smaller. Exactly. You can organize these things, and in some sense, the mass is sort of it's different. Yeah. I'm not sure what I say exactly. It's a different orbit.
You
Yes.
organize them in parabolic, hyperbolic.
There are two SL2, right?
There are two SL2s. Yeah.
So you could have singularities not at the same time, at the same.
Good. So the difference between those two singularities is sort of the angular momentum of the black hole. If that makes sense. If the holonomy is different, that means that it's rotating in one direction, basically. Yeah, that's right. So I mean, if you had one of them regular and the other singular at one point, it would be an extreme limit of that case, basically, extremely rotating. Okay. Good. So now, so everything I've said is very well known. So we should be able to reformulate the Ryu-Takanagi prescription in the Chern-Simons language. Okay? So this is just a rewriting of ordinary known physics. The question I'm asking is, what is a geodesic in this formulation? Okay, in the Chern-Simons formulation, how do I think about a geodesic length? Okay? So a geodesic is some point-like object, it's some line-like object in the bulk. So it seems clear that I should be thinking about Wilson lines in some representation of SL2. That's really the only gauge invariant object I have to play with. It seems clear that should be involved in some way. So here's a Wilson line. You can write it like this. It's a trace in some representation of the path toward exponential. So really the only question is, what representation do I use? What is the right representation to capture the information of a point particle, the geodesic? So this is, really I'm just asking, how do I couple point particles to 3D gravity in Chern-Simons formulation? This was worked out in great detail in the flat space case by Whitten and Carlip, again in the 90s, I think. And I'm just going to take things that they did in the flat space context and translate them to the ADS context. So first of all, point particles carry mass and spin. Okay, so there are numbers that are associated with this point particle. The particle moving in the bulk, its mass and spin control how it interacts with the geometry. This information must be stored in the representation. Because if you think about it, there's nowhere else for that information to sit. The representation must store that information. So when I think about representations of SL2, my first thought is to think about the finite dimensional representations, the vector, the adjoint, etc. However, if you think about it, each of those representations does not have a natural space for this number to sit, this mass or this spin. Also, they're not unitary, which might bother you. So if you take these ideas seriously, you realize that we shouldn't be thinking about the finite dimensional representations of SL2. There are no natural numbers characterizing them, and they're not unitary. They're probably not the right things to think about. However, there do exist other representations of SL2 that are not finite dimensional.
Right.
Yep.
Two particles without spin but different masses
Yeah.
will follow the same geodesy.
Oh no, you're right. Yeah, but for example, if you're interested in the back reaction of the guy on the geometry, then the back reaction will be different, and that information should be stored in this Wilson loop, basically. So you're right. They'll follow the same geodesic, but they interact with the geometry differently, and so the information should still be there in this thing. That's right.
So you assume the mass can vary continuously.
I do. Yeah, I think actually.
Finite dimensional positions have discrete integers.
Indeed, you're right. So I would like to have a formalism where I can take the mass to vary continuously, and you'll see that the formalism I use does allow that. But if you think about it seriously, think about it carefully, I believe it's again quantized, and we can talk about that after. But basically, I would like to have a formalism where I can let the mass vary continuously, at least in the limit of large mass. That should be something possible in the limit of the formalism I'm using. What I will do will allow that.
Can the spin also vary continuously?
We're working on that right now. It's a little more complicated, but I would, again, you might hope to have a formalism where this is possible. Yeah, that's right. Yeah. But I think we can do that in this turns out. We can talk about that after, yeah. But yeah, what I'm going to do now is keep the spin 0 and vary the mass continuously.
You should also have some formulation for non-abelian anions, which would be much more interesting.
That would be more fun. Yes, there's some non-abelian character to this already, I guess, because it's SL2. But yeah, indeed, yes, there should be some formulation of non-abelian. I think a lot of what I'll say for compact groups is much simpler, which is the normal setting for non-abelian anions. So some of the complications that I'm going to talk about is because this SL2 is non-compact. So, but indeed, there should be a formulation for non-abelian anions. Okay. Good. Other questions?
You have an expression for the metric out of gauge field.
That's right. Yeah.
So you have, in principle, geodesic motion you can address there.
Sorry.
You can address the geodesic over this metric.
Yeah. Yeah.
How are they compatible with it?
Good. No, good. Very good. I will show that they're compatible in a couple of slides. But I agree that right now what I'm doing doesn't seem obviously like it's going to result in a geodesic. So I'll show that it does. But it's a bit non-trivial, actually. There's some steps. But basically, I want to express precisely that idea in the Chern-Simons language, because for higher spin gravity, we need to use the Chern-Simons language. So that's why I'm sticking with the Chern-Simons language. But it will eventually reproduce normal geodesics, as I'll show in a couple of slides. Yep.
So is this spin bigger than 2?
Sorry? The spin bigger than 2? So right now, I'm only discussing ordinary Einstein gravity. So I just have a metric with spin 2. However, right now I'm thinking about a particle moving in the bulk. You could imagine that particle having a spin as well. However, I'm going to focus on the case where that particular spin is 0, the spin of the particle. So does that answer your question? I've not gotten into the higher spin stuff yet. That will come in a couple of slides. Okay, so let me remind everyone what the highest weight representation of SL2 is. So this should be familiar from conformal field theory. So the highest weight representation of SL2 is the following. You take, consider you have a ground state, let me call it H, which is an eigenstate of L0, which is annihilated by L1. And then I generate a tower of states by acting with L-1 on this guy. I generate an arbitrary tower of states. This goes on forever, because L-1 will never annihilate this, so I create an arbitrary tower of states. And the energy of each of these states, the eigenvalue under L0, goes up every time I act with L-1 on it. So I generate an infinite, a huge tower. So this tower is nice. It forms a unitary, infinite dimensional representation of SL2. Okay. And the representation is labeled by the value of the Casimir, C2. And C2, this guy commutes to all the generators, and so it's the same on every state in this tower. And so you can, for example, evaluate it on the ground state, where you find that C2 is related to the energy of the ground state in this way. Okay, so it's a number characterizing this representation. So you see.
Why should you want the highest weight representation? There are other unitary representations which we can mention.
Good. So the reason why I think I like this one is that this particle, this guy moving in the bulk, should capture the same physics in some sense as the single particle sector of a quantum field theory living in the bulk. I know that I can organize that quantum field theory, the single particle states, in terms of the highest weight representation. So that's why I'm partial to the highest weight representation. That's right. There are indeed others. I don't really know what they all mean, actually. But this is the correct one if I wanted to, for example, have an ordinary particle in quantum field theory on ADS3. So that's why I think these are capturing the same physics. That's right. That's right. And you'll see that a lot of things will follow very naturally from this choice. So that's again why I think it's correct.
You're implicitly assuming that K is large?
I haven't really assumed it yet here, but I'll tell you when I assume it. I'll assume it at a certain point. Yeah. But certainly, I'm freezing all the gauge fields. I'm going to keep them all fixed. So I guess that actually does mean that K is large throughout. Good. So this is a representation. It's a nice one, and I claim that this is the appropriate representation to use if you want to capture the physics of a heavy particle moving in ADS3. And again, most of these ideas really follow from these old papers by Whitten and Carlip on the flat space version of this story. Okay. And so what I need to do is compute a trace in an infinite dimensional representation of a gauge field. And this rep is characterized by two numbers, h and h bar. So the energy of the highest weight state in each under A and A bar. And in the ADS-50 context, it's sort of easy to see what this corresponds to. These correspond to the conformal dimensions of a putative dual operator. Okay, that's the information stored in H and H bar. And in the bulk, they're related in a sort of obvious way to the mass and the spin of the particle. Okay. Now I claim that if you compute such a Wilson line, where you anchor these 2 points on the boundary and have the Wilson line moving through the bulk, what this Wilson line will compute for you is the proper distance through the bulk between these 2 points. It's, in fact, in a certain limit, it's exponentially small in that proper distance, and the precise dependence is this, where C2 is the Casimir of the representation. If you instead loop this guy around a black hole, then it will give you a non-zero answer, which measures the horizon length, and thus the entropy of the black hole. That's what this Wilson line does.
So where's the information that this is separated by distance A?
You need to specify boundary conditions on the guy at infinity. That's what carries that information. On this, you'll see, I haven't told you yet quite how I'm going to take the trace. In taking the trace, you need to specify a boundary condition on a certain thing, which I still haven't told you about. I'll answer the question in like 1 second, yeah. But in here, it's easy to see how this works for the black hole. Yeah, good. A sort of fun thing about this is all the connections in the bulk are flat, and thus the actual trajectory the Wilson line takes doesn't matter. So, I mean, I drew this in this curvy way, but you can imagine it being a wiggly path like this, and it must still give the same answer. Okay? And similarly, you can do anything you like around the black hole. It'll always give the same answer. It always tells you what the horizon length is, even though your path doesn't care. So it's because this formulation of the theory is purely topological, this must happen. But it's sort of fun that it actually does work out like this. Okay. So let me now justify this statement. Okay. So I'm going a bit slowly, so I'm going to go a little bit quickly through this, but I'll justify this statement. So here's a question. How do you take a trace in an infinite dimensional representation? Okay. So this sounds kind of hard. You have to sum over infinitely many states. But it turns out there's a physics way to do this. We're going to do this in a physics way. And in a physics, we're used to infinite dimensional spaces. They come up all the time. They're usually the Hilbert spaces of quantum mechanical systems. Okay. So what I'm going to do is generate this trace by introducing an auxiliary quantum mechanical model that has this representation as its Hilbert space. Then I'm going to I'm going to do the quantum mechanics with that theory, and that will do the trace for me. So let me now tell you what the quantum mechanical theory I want. Consider the group manifold SL2. Take a particle, I'm going to call it U, living on that group manifold. Okay. So U has a natural action, okay, which is covariant under group actions of SL2. The action looks like this. So S is just the particle moving in SL2. S is some time, and U lives on SL2. This trace is something that's nice because this action preserves the following global symmetries. I can act on U from the left and from the right, and thus the isometry, the symmetry group of this quantum mechanical theory is 2 copies of SL2. Okay. And so now you can take this theory and quantize it carefully. It was done by these people. And you can show that if you quantize it carefully, the Hilbert space of this model is exactly the highest weight representation that we want. Okay? So this Hilbert space carries the information. It has all the states that we need to sum over. So now I want to use this to actually do the sum. So how do I do that? I need to somehow take the gauge fields that I have and couple them to this model in some manner, and then use this model to compute the trace. So there's really only one way to couple 2 gauge fields to this model. What you do is, you have this world line moving in the bulk. So I have this X. X parameterizes the world line. At each point on this world line, I have an extra field U, where U lives in SL2. Now I can couple that field U to the gauge fields by replacing the derivatives here on this page, D, normal derivatives, with covariant derivatives using A. And then, what I'm going to do to take the trace is perform the path integral over the field U. That will simply take the trace over the infinite dimensional highest weight rep and give me an answer for this Wilson line. And again, this is basically a Witten trick that we're generalizing here using here to take this trace. So, this is the thing. I claim if you do this, it exactly takes the trace that you want. Now, for an open Wilson line, you have to do a little. So, for a closed Wilson line, this is a completely well-defined procedure. For an open Wilson line, you need to do a little bit more. You need to specify some boundary conditions at the endpoints. this is related to your question. This is what tells you what the distance is between the 2 points. This choice of boundary conditions and where you do it. So the boundary conditions I'm going to use are the following. There are various ways to justify this, which I'm happy to talk about, but it'll take me a little bit far afield. But for now, this is the boundary condition I'm going to use, that u is 1 on each end of the Wilson line. Now, while you can, in principle, do this thing exactly, we're going to evaluate it by saddle points. So instead of doing this full path integral, I will find a classical solution to the equations of motion of u and evaluate that guy on shell. And that will give me an answer.
Sorry, can I ask a stupid
Yes,
question?
yes.
So in the quantum mechanics, u is the dynamical variable.
That's right.
Where does the information c go into the quantum mechanics? That's some fixed background x?
The information c of, sorry, you mean
The curve c.
Oh, the c, good. It comes precisely through here. You see A is a gauge field living in the bulk. Now I pull back A onto the world line of the particle by doing this A gamma, contracting it with the world line of the particle. So
X's are the same as u's, x is just...
they're not actually. Good, so let me be careful about this. X is really ADS3. Okay, so the trajectory I take through ADS3. U is some auxiliary quantum mechanical variable. It's some abstract thing. So they have nothing to do with each other, actually.
So from the perspective of the quantum mechanics,
Yeah.
u is a dynamical variable.
That's right.
X and A I should think of as sort of background source.
Exactly. That's exactly right. Yeah, that's exactly right. Yeah. So that's how it enters, through this coupling.
So U only lives on C, is that right?
Sorry?
U lives on C.
Correct. U lives on C. Exactly. U lives on C. That's right.
What controls the saddle point?
Controls what? Sorry, the saddle point?
Yeah.
Good. The saddle point is good when the Casimir of the representation is very large. And in the application to entanglement entropy, that will end up meaning the central charge is very large. That's what we'll call the saddle point. Good.
Is there supposed to be a mass hiding in here?
The mass is hidden in this SP thing here, where it's in SP right here. Yeah, that's right. That's where it's hiding. Yeah. So you can see why when that's large, that's where saddle point is good. It's a heavy limit, the large mass limit. Okay. So now, okay, good. Let's now do this saddle point thing. So I'm looking for solutions to the equation of motion. So you can write them down fairly compactly. They look like this, where d is that covariant derivative. But actually, these equations for any reasonable choice of A, and pretty much any choice of path, look really, really complicated if you actually think about them. Because my path, I can take it however I like. It's, you might imagine I just take it hugging the boundary or take it something else. But the equations of motion look very, very different depending on how you take the path, because they see the bulk gauge field differently depending on how you choose the path. So these are quite complicated. So what I'm going to do is try to find the trick. Let me try, just out of desperation, to look for a really simple solution. The solution will be the one where this guy doesn't move at all, where u is equal to 1 at all points along the trajectory. Okay? This is not empty. If you just plug that into the equations of motion right in here, and you work out what you get something that looks like this. Okay? So this isn't empty. In fact, it's a differential equation for the path. Okay? So that's kind of interesting. What this is telling me is if I choose my path to follow this particular, to be a solution to this differential equation, then I do have a solution that u is 1. Now, what is this differential equation? A and A bar are the bulk gauge fields, but I can relate them to the ordinary metric fields using the dictionary I told you earlier. And if you do that, what you find is just this. So this equation is the same thing as the geodesic equation in the bulk. Okay? So what this is telling me is my calculation is easy if I take my bulk trajectory to follow a geodesic. Then the solution is u equals 1. So this is the bulk geodesic equation, and it just dropped out from this formalism. If I take any other path, I must get the same answer, but the calculation will look very different. In particular, u will vary in some complicated way along the path. So this is it.
Is the path independence of WC obvious from this auxiliary quantum mechanics?
Obvious. I think, well, so you might need to work a little bit. I mean, it's only true if the connections are flat. And so you could imagine doing this auxiliary quantum mechanics trace with any choice of A. And so it's not built into that part of the formalism. But if the connections are flat, I think gauge invariance does imply that it must be path
Are you
independent.
not assuming or proving some non-abelian version of Stokes' system?
Good. I think that I'm not, actually. I think that I'm not.
I mean, that's what typically Stokes' in abelian
Yeah.
theory. Stokes' theorem says it's independent of the path if the connection is flat.
That's true. That's
So
true.
that's what we've got some non-abelian version.
No, you're right. Maybe there's a relation. I guess you're right. So that's true. Yes, I agree with that. So what we have done explicitly is We have a way to compute this which manifestly shows that it doesn't depend on the path. There's an alternative way to compute. But I think you're correct. Yes, that's right.
Isn't this choice of view just that you're aligning the auxiliary SL2 with the SL2 of the isometry group?
Probably. I'm not quite sure how to think about that. That's probably true. Yeah, I think that's right. And you can only do that if you move on a geodesic. That's probably correct. But I don't know quite how to make that precise, actually. And you'll see that this trick won't work in the higher spin case. Yes, David.
You required h equals h bar in order to hook up this auxiliary quantum mechanics.
Yes.
Is that right?
Yes, that's
and
absolutely
if h
right.
is not equal to h bar, do you have an analogous?
It's a great question. We're working on this. You can do the Chern-Simons. You can get answers, but it's hard to interpret them from the metric point of view. Basically, that's where we stand right now. But you can get answers. It's this step that I just did right here is very difficult for that case. If h is not equal to h bar.
The answer should be whatever the geodesic followed by an anion in the bulk is.
Yes, that's correct. Yeah.
You know the answer to that?
We're working on that as well. We do not know the answer to that. That's exactly right. That should be the answer, and it's surprisingly complicated to answer that question. Yeah, but we're working on it. Great. Yeah. Good. Okay, so this is the bulk geodesic equation. Okay. So it's sort of nice where this came from, and indeed, if you now so this is what I said a second ago, and indeed, if you work out the on-shell action, it's manifestly equal to the proper distance along the path. So this is entirely equivalent to the normal story of particles moving in ADS. We've written it in a different way. And so it's kind of nice that this notion of geometry just sort of dropped out of the Chern-Simons formulation. And now you can apply this to the computation of entanglement entropy. What that really boils down to is fixing C2 in the right way. And you can do that by appealing to the replica trick approach to computing entanglement entropy. So basically, we can completely reformulate entanglement entropy in this Chern-Simons language, and it's not hard. It involves doing all these steps, but once you do that, it's not hard. Okay. So let me just summarize what we just did. I reviewed how ADS-3 gravity works in Chern-Simons language. We found a specific choice of Wilson line, which is related to entanglement entropy, which I motivated in various ways. And I computed the relevant trace in a saddle point limit. I argued it really does compute the proper distance, and there's a fun way to see that, which is if you take the bulk path to follow a geodesic. Okay. So we're done with spin 2 gravity. Now on to higher spin gravity very quickly. So because I'm running out of time, I'm going to explain higher spin gravity ADS-3 to you on one slide. So this is a complicated subject, but remember I said that the action for normal spin 2 gravity could be written as a Chern-Simons form. All you do is take your SL2 and make it into an SLN. And then you get a theory of higher spin gravity containing fields of spin going all the way up to n. So the Vielbein is the difference of, you can still construct a sort of generalized Vielbein, which is the difference of A and A bar. And now you can make a metric, and which is the trace of E squared. However, now I can take the trace of E cubed. It's a different matrix now, and I get a spin 3 field. I can take trace of E to the 4th, blah, 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 all the way up to n. They'll all be different non-trivial matrices, which will all give me different fields. So in this talk, I'm going to focus on the simplest case, which is n equals 3. So I'll have one extra spin 3 field. That will be pretty fun by itself. Although in principle, you can generalize this to any as high n as you like without too much effort. So I'm going to tell you a little bit about how higher spin theories work to explain what I'm going to calculate. So if you have SL3, every way of embedding SL2 into SL3 will give you a different notion of metric. Okay? You should imagine them as being different vacua, different CFT vacua dual to the same bulk theory. So for SL3, there are two ways to do this. They're called the principal and the diagonal embedding. And in the principal embedding, if you decompose your fields into how they transform under SL2, you get a spin 2 and a spin 3 field. And there's so the central charge of the theory is related to the Chern-Simons level, why a formula looks like this. And this is called the principal embedding. It's a very nice embedding. There's another one, which is in some ways less nice, called the diagonal embedding. It's called diagonal just because of how the matrices fit inside the larger matrices. If you do the same game of looking at how your fields decompose under SL2, you find instead of a spin 2 and a spin 3 field, a different decomposition. What I want to draw attention to is that there's a spin 2 field and some gauge fields, some U1 gauge fields. It'll play an important role. And the central charge is related to the level in a different way. An important point here is that this vacuum is actually not unitary. What that means is these Chern-Simons fields are dual to a Kac-Moody algebra on the boundary. That Kac-Moody algebra has a level which is negative. And so there's something weird about this theory. This will come back in a second to bite us. Okay, but this embedding seems completely fine. So, and what I emphasized earlier is that the higher spin gauge symmetries act on these fields in a complicated way, and the metric is not gauge invariant. So quickly now, let me talk about black holes in higher spin theories of gravity. You can think about them in the same way you thought about black holes in the lower spin theory if you use the Chern-Simons formalism, except that now, again, there's a non-trivial holonomy, there's a sort of defect, the holonomy is non-trivial, except now the holonomy is an SL3 matrix and not an SL2 matrix. The extra information in that matrix is the higher spin charge carried by this black hole. So they can carry higher spin charges. And these black hole solutions have been constructed. And what's interesting, again, is that the higher spin gauge transformations really act in a peculiar way on these black holes. They make the horizon go away, and geometry has become confused. However, our way of formulating this Wilson line, this entanglement entropy as a Wilson line, generalizes completely naturally to higher spin theories of gravity. There is no problem in generalizing this to a highest weight representation of SL3 instead of one of SL2. So our proposal is simply the following. The Wilson line in the highest weight representation of SL3 is the generalization of the Virutakinagi formula to higher spin gravity. It's really, I think, the only reasonable generalization of the higher spin of this idea. And it actually does implement, so we just thought this was a natural generalization and we studied it at great length. But while this was going on, this paper by Lukowitz and Maldacena appeared, sort of telling you how you could try to derive the Virutakinagi formula from a replica trig approach. So we thought about it, and actually, this Wilson line implements that replica trig approach to computing entanglement entropy. It's actually the same thing. And I'm happy to talk about how that works if you have questions, but it'll take us a bit far afield. And finally, there's a different proposal in literature for this higher spin entanglement entropy. It involves a finite dimensional trace instead of an infinite dimensional one, and it involves some other manipulations. So the starting point is actually very different, but the final answers are actually always the same as everything I'm going to report here. So I'm not really sure what's happening there, but there's a different proposal which I encourage you to read. Yeah?
When you say implements replica trig,
Yeah.
What do you mean? Are you able to write Riemann entropies?
No, good. So what I mean is, if you look at the paper by Lukowitz and Maldacena, then they argue that in the limit that n goes to 1, if you're doing the replica trick, in the limit that n goes to 1, you can understand the geometries in the bulk in a specific way and compute their action in a certain approximation as n is close to 1. Ours is similar to that. It does the same thing, and that it generates a conical defect whose opening angle, if as you take n to 1, is closing up. So to the extent that you believe the Lukowitz and Maldacena proposal for computing entanglement entropy, this is of the same flavor. That's pretty much all I mean by that. Yeah. And actually, so this is actually useful, this way of thinking about it, because you can use it to, this is sort of what you use to fix okay, let me explain this slide, and then I'll come back. I'll go again quickly through this. So we do this the same way as before. You have an auxiliary quantum mechanical system where U lives on SL3, except that now we have some extra Casimirs. We don't have just one quadratic Casimir, we have a cubic Casimir as well. So we need to fix that cubic Casimir, and in fact, we fix it to be 0. Okay? And we fix the quadratic Casimir to relate to the central charge. I did this in the previous SL2 case as well. And one way to understand this is to demand that the singularity that this Wilson line creates, the back reaction of this Wilson line on the bulk gauge fields, is that you expect from a conical defect moving in the bulk. And this is related to the idea of Lukowitz and Maldacena to understand the replica trig approach to computing the entanglement entropy. I want it to be only a conical defect and not source any of the higher spin fields. That's why C3 is 0.
Now you have chosen one of the two embeddings.
This is true for both embeddings. This information is actually invariant under the embedding. That's right. Yeah, it's true. It's not obvious that it is, but it is invariant under the two embeddings. The prefactor that you get here does depend on the embedding, actually. But this fact is true for both embeddings. Good. And this is just what I said. You can understand this from the replica trick if you want. From the field theory point of view, what you're just saying is that the endpoints of the interval, in some sense, that I'm computing this on, don't carry any higher spin charge.
When you say it creates a conical singularity in the bulk,
Yeah.
you mean that if you took into account some kind of back reaction
That's
on
right.
which you're not going to do in your calculation.
I won't do it in the calculation, but you can imagine just differently. I have this action, the Chern-Simons term, plus this particle.
Yes.
You can just vary that action with Chern-Simons term and look at the holonomy the particle creates in the Chern-Simons term.
Right, and then it would have this
Then
effect.
it has this effect. That's right. That's how I picked
I'm
it
just
up.
curious, are you saying that you have checked that if you study the back reacted solution and compute the action for it,
No.
same result, a la Lukowitz and Maldacena?
I have not checked that in detail. Good. I've not checked that.
There's a
in detail, that's
calculation
right.
there for someone to do.
Yeah, that's right. Is there something to do? We have not done it in detail. Yes, I think that is morally correct. I think that's what this is doing. But it's that's right. Yeah, good. So okay. So now let's try to solve the equations. Now you have some equations. They look the same as the old equations, but the fields are just bigger. So for example, we could try the same trick. We could try to set U to 1 and look for some sort of new geodesic equation in the bulk. However, this equation looks the same, but actually its interpretation is very different. And the reason why is that A and A bar now are not SL2 matrices, but SL3 matrices. And thus this equation actually now has 8 components, not 3. And so if I just vary the x's, that's varying 3 variables. And that's actually not enough information to find a solution to this equation. That's not enough degrees of freedom, because this is an 8 by, this is a, it's a 3 by 3 matrix with 8 equations. What that means is, if I ever turn on any higher spin field, if ever A and A bar don't just live in an SL2 subgroup, I cannot use my geodesic trick to solve the equations of motion. So I have lost the geometric interpretation that I had in the previous thing. So I think this is kind of interesting and nice that the geometric way of thinking about it actually just pretty much immediately breaks down here. And it would be fun to try to generalize this and see if you could, what the minimal ingredients are you need to think about this in a space-time way. But actually what we're going to do is we're just going to find solutions to this U of S in some different manner, which I'm not going to tell you about. But you can do it, there's a trick to do it, and it's not too hard, but you can just find solutions in some different manner, not going through a geodesic equation. Okay, so now here are the answers. Quickly. So I'm going to discuss them in order of increasing complexity. So first, the diagonal embedding. So remember, in the diagonal embedding, I have a spin 2 field, gauge field, and some other fields. So first, to warm up, let's just embed our normal SL2 solutions inside this SL3 and make sure it works still. It will not surprise you that it does work still. You can find the geodesic with respect to this new metric, G. But I haven't turned on any higher spin stuff, so it makes sense that this should work. This is really a 0th order check. Now, one thing I can do to this black hole is I can turn on a holonomy for this U1 gauge field around the black hole. That is the analog of higher spin charge in this embedding. So I can turn on this holonomy. Now, that holonomy of this U1 charged field around the black hole changes things. It changes the computation. And in fact, it removes this geodesic interpretation. I can no longer interpret it as a geodesic. However, the answer stays the same. Okay? And this is actually what you expect. Because turning on this holonomy doesn't really change the physics in any way. It shouldn't change anything. But it's actually non-trivial that it happens from the higher spin point of view. Different fields appear, but they all cancel from the final answer. So this is already a little bit of stuff is happening, but it's it's kind of the same formula, so it's not that exciting. So let's move on to the principal embedding. Okay. In the principal embedding, I have a spin 2 and a spin 3 field. So again, the things that are an SL2 subgroup all work out. That's fine. But now we can study a spin 3 charged black hole. This is a different and non-trivial solution. Okay. You can take your node BTZ black, take your CFT action, deform it by the spin 3 chemical potential, and you get a different action. And this chemical potential gives the black hole spin 3 charge. An important point is this deformation is irrelevant. W is a spin 3 current. And so the UV structure of the geometry is completely modified. And we will come back to this later, but for now let's just stay in the infrared. And so you can compute the entanglement entropy. If you separate the intervals by a large distance, you find that indeed the entanglement entropy begins to grow linearly in the separation, as you expect. So you could read off an entropy density from this formula. So this is the expected structure. But now you can ask, does this coefficient actually match with the thermodynamic entropy, which you can compute in other ways? Now the problem is actually that you can compute this in many different ways, and they don't all agree with each other. So there are at the moment 2 different answers for the thermodynamic entropy. There's a UCLA answer, which I'm calling because it was worked out by the UCLA group first. This was the first answer computed. And there's some answer that you get from thinking about the bulk thermodynamics in a way that I feel is very sensible. And you can even you can generalize this, and you can even do CFT computations in a theory with a different symmetry algebra, but which is expected to reduce to this theory in a limit when you set a certain parameter to 3. Okay? So there's some answer. There's some nice consistency here between these 2 things. However, some different groups also tried to compute this. They did it in a different manner. They worked out a walled entropy by expanding things order by order and trying to write things in a metric formulation and then expanding order by order in the higher spin fields. They got an answer which is different. Further work so this is a perturbative calculation in the higher spin charge, but further work showed how to get that answer from the Chern-Simons point of view and demonstrated how this is also seems to be consistent with the notion of bulk thermodynamics. And finally, you can try to apply the conical singularity method to this calculation. I put it in the middle because this involves regulating a singularity. I think the right way to regulate the singularity is not really, well, it involves things similar to what I'm talking about, and so I'm not quite certain how to interpret this answer, but if you look at this, you can, this seems to agree with this one, but I'm not completely certain that this is the case. Yeah.
UCLA entropy satisfy our first law?
Yeah, so the way in which these are computed is that you take E and you use the first law.
The wall entropy is computed in that way.
Oh, so the walled entropy is actually computed using the walled formula in the perturbative calculation.
But the wall entropy is guided by the first.
Yeah, you're right. The walled formula is guided by that. Yeah.
UCLA entropy, does it satisfy our first law?
It does satisfy first law. The real issue is that the notions of energy that you want are a little bit confusing. That's really the issue here. That's right. So presumably the notion of energy the walled entropy uses is actually not the same as this notion of energy, I imagine. Yeah. That's really the issue here. So our calculation, it does agree with one of them, which I guess is the most that we could have hoped for. It agrees with this one. So that's nice. It does agree with this. And the real issue is especially this. There are multiple notions of energy and thus different first laws. And there's been a fair amount of work in this. Our prescription doesn't know about that. It doesn't know about energy. It doesn't care. It's a calculation that just happens in the bulk. And so it's independent of much of this discussion, I feel. So this remains to be sorted out. I think it remains to be made clear precisely how these things are related.
Why is there an ambiguity in the definition of energy?
It's a good question. It's quite complicated. You need to identify the boundary charges in the right way. There are apparently multiple ways to do that. So I should admit that I'm not completely sure what.
It's a matter of how you pick out a cell, some sort of gravitational subgroup of the higher spin.
So I think it's not actually that. I think one way to think about it is that when you go, let's see. So the most recent understanding I have of this is that when you go from a Hamiltonian to a path integral formalism, then the notion of the chemical potential that you're inserting is a little bit different. It's not. There's some subtlety in going from the Hamiltonian. You take each of the beta h plus mu times this chemical potential. When you go from that to a path integral, you introduce extra terms, which might mean that you have misidentified the relation between the energy and the chemical potential in some manner. So I should really say that I'm not actually familiar with. I've not been following this story very closely in the recent literature. So I should direct you to Eric afterwards, who has been. He can explain, but I'm not exactly certain. That's right.
But haven't you chosen secretly a notion of energy? I mean, you've chosen a conical singularity and a space-like slice with a compact.
Good. So
t side in the t direction.
Well,
that chooses energy for you.
So I don't actually think so. The notion of energy that I'm talking, this ambiguity I'm talking about, is quite subtle at the boundary. It's not related to this sort of choices. I've really made very few choices.
The black hole, not the energy of the probe.
Oh yeah, and that too. This energy that you want is the energy of the black hole. Yeah, that's right. That's an important point too.
You have a background connection, and you have to tell me how the coefficients in that background connection are related to physical quantity.
Yeah.
And that's where
this ambiguity comes in. The dictionary isn't quite understood precisely yet. Yeah. Very good. 5 minutes. Let me move on. So this is still a controversy, and I'll admit that I don't fully understand what's happening here. Okay. But ours doesn't. It's not. I don't think our proposal really knows about these subtleties in the boundary charges. I don't think we're not picking that in this thing. There's really very little that we pick. It's really enormously rigid. And one way to see that is this: when we first started, this formula was known. These were not as this. Only the first order formula was known, and so we spent a lot of time trying to make our thing, agree with the earlier formula. So it's really quite rigid. There's, as far as I can tell, no way to do that. Our formula really does agree with this one. So finally, remember I said the chemical potential is irrelevant? That means that in the UV, my theory is becoming completely destroyed. And in fact, it turns out that what happens in the UV is that it flows to the other vacuum, the diagonal embedding vacuum of the theory. So what that means is that if you are at zero temperature, this theory, what I'm describing, if I keep the chemical potential non-zero and go to zero temperature, is a flow from the UV to the IR, where the UV theory is the diagonal embedding and the IR theory is the principal embedding. All right. Now, you will note that the central charge in the UV is less than that in the IR. This is weird. It's a possible conflict with common sense, but it doesn't break any theorems because the deformation, the chemical potential actually breaks Lorentz invariance, and so the normal theorem doesn't apply. And in fact, the UV theory wasn't unitary anyway, so probably that means that the theorem also shouldn't apply. This still bothers me a little bit. It might indicate something is funny with this, but it's a fact that you can write down a solution which interpolates between these two things.
Why is UV theory not unitary, and why isn't that bad?
It's bad. It's bad. Yeah, I'll show you. The badness appears in the calculation in a second. You could be bothered by it, but the solution you write down that does this interpolation, it looks fine actually. The solution does look fine. So bad. How does one define bad? I guess. So.
Sensible theory.
Yeah. I mean, I'll present a badness in our calculation that I think can be traced to this in a second. So that might be another way to see it.
This isn't a. Sorry, Doctor.
This is a symptom of the entire higher spin setup here, or?
Oh, no. It's only that particular vacuum. So you always have one vacuum which is unitary, which is perhaps all you might want to work for. It turns out that the principal embedding is fine. The diagonal embedding vacuum is non-unitary. That's correct.
That was the ill-defined theory of this flows to.
Yeah, it flows to some theory in the IR. Yeah. So yeah, you could be skeptical. Indeed, you could be skeptical. The bulk solution looks regular. So, but nonetheless, I'll show you in a second that maybe there are reasons to be skeptical of this. But yeah, the solution exists. It seems like a regular bulk solution, so it makes sense to calculate this thing on that background. It's a reasonable thing to be worried about. Yes.
Are there no black hole solutions that just use the principal embedding?
So they all break down in the UV because there's ones without higher spin charge, but the higher spin chemical potential is irrelevant, and so you lose control of them in the UV. So you can just drop the UV if you want, and then you can just think about IR problems, which is, I think, a sensible thing to do.
There are no known black hole solutions which are good in the UV.
Good in UV, yes. I think that's correct.
In the higher spin.
In the higher spin theory, yes. But that makes sense just from dimensions, because the dimension of the charge is 3. So I think that's just a fact. That will just happen. Because the chemical potential is a spin 3, is a spin 3 chemical potential, and so you are stuck with that fact, I think. Okay, so
Put that back if you want to work in a canonical ensemble. I mean, you could have a black hole with charge and no chemical potential.
Well, that's part of.
So this is the issue, I think. This is the part of the controversy, basically. So this is a good point, but this is related to this controversy.
If mu makes the theory flow, or if it preserves
Yeah.
the W3 symmetry, the initial symmetry.
Yeah.
And that's why these two groups are fighting.
Yes,
Like,
yeah.
that's,
You see how you might get concerned.
So naively, mu will make the theory flow,
Yeah.
because it's an irrelevant deformation. But the other group, like the other side of the flag, are arguing that it doesn't make the theory flow. That's why their definitions are.
Yeah. So you can see how you could get into complexity. Yeah. So because I'm running out of time, let me just flash a thing illustrating how this here might be bad. So let's just compute on this. Okay. It's easy to compute, and we get this. Okay. This is the entanglement entropy plot as a function of interval length. This looks weird because something very bad happens here. Okay. And so what's happening is there's a peculiar kink at this intermediate length scale. This length scale is set by the chemical potential. In the long IR, it's fine. In the UV, it behaves kind of badly. First of all, strong subadditivity is violated because the entanglement entropy goes down. In an infinite system, the entanglement entropy cannot go down. It must always grow if you have a system satisfying strong subadditivity. So I break strong subadditivity here, and the kink is also sort of a singular violation of strong subadditivity. So this whole region is sort of very unpleasant right here. And I think this is related to the fact that the theory is bad. So maybe this is one reason to think the theory is bad. It's kind of interesting this happens even though the bulk solution looks completely regular, though. So it's sort of a subtle diagnostic. And so I think that there's still more to be understood here. But right now I'll say this is the UV CFT is not unitary, and this is why this is happening, I believe. And we're doing further calculations on related backgrounds to try to understand this a little bit more. Okay. Good. Dotted curves are, so I haven't gone into this in this talk, but there are multiple inequivalent solutions to the equations of motion. You can fix one of them by demanding continuity with the limit that you want, the SL2 limit. That's the solid black line. Dotted curves are the other solutions, and so I can explain in more detail what they mean, but they're not related to entanglement entropy. But I've included them on this plot just for completeness. Good. Okay. So I'm not going to talk about the direction. There's many fun things one could do, which I'm happy to talk about. Let me just summarize and conclude. So the thing that we found a prescription to compute entanglement entropy. There are many fun things you can do with this. And I think it still remains to be seen if we can push this further and see what insights this gives about how geometry emerges from field theory. Higher spin theories are sort of more solvable, and you might expect you could get more about this emergence from this point of view. Thank you.
One question? This nice RG flow you have, I don't think it's bad. I think it's good. You've got an example of emergent unitarity.
Okay.
I don't know what that means, but it sounds interesting.
I see. Emergent unitarity. Very good. Very good. Okay, yeah, why not? That's right. All the negative norm states decouple. You restrict the low energies with sector of states. Yeah, there we go. That sounds good.
Probability is concerned.
That sounds good. Okay, I like that. Here we go. It's a great example of emergent unitarity. Yes. Okay, thank you.
Are there any ways in which you can generalize this to higher than 2 dimensions on the band?
So I don't, it's not as obvious to me actually. We were really lucky here because this gauge field representation of the theory is really very nice. You have a lot of intuition with gauge fields. To higher than 2, and in the bulk you get, the 4D Vasiliev theory, and I really don't know how to think about that in any geometric manner at all. Here at least I knew what the right object was. It was a Wilson line. There, I really have no idea. So
What's the obvious thing to think about is to generalize the gauge field for twofold.
good. I do not know if the Vasiliev theory has a representation in that way. I'm not sure.
So is there any known example of a non-unitary CFD where strong subadditivity is violated?
I think people don't study non-unitary CF. Well, like maybe they do. I'm not sure actually. No. So maybe you're right. No, they do actually. So, but I've not come across one. That's right.
Isn't the statement
I don't know.
that in the Vasiliev theory you cannot truncate the finite m?
In the Vasiliev theory, you cannot truncate.
You cannot
That's right.
truncate to finite spin.
You cannot. That's correct. That's correct. Yeah.
I don't think that's good.
Sorry, what?
I don't think that's. I thought that was a problem.
In D equals 4, you cannot.
That's true.
Yeah.
D equals 4.
Yeah, that's what I meant.
That's what you're talking about, right? D equals 4. Yeah. In D equals 4, you cannot. Yeah. In D equals 3, we have. Yeah. That's right. That's what we've been working with. And yeah, so it's a good question. I don't know. It should. Yeah.
But the question is whether your observable is really represents entanglement or not, right? Because if you can show that in all theories, unitary or non-unitary, entanglement has to satisfy strong subadditivity.
So I think you can, because there's an inequality in the strong subjectivity formula, and that's because I think states have positive norm. That's where that inequality, that's where the positive greater than 0 comes from. So I suspect that you cannot. Now, it's a different question whether that non-unitarity actually encodes itself in you're doing a very specific division of the Hilbert space into spatial regions, and so maybe there you could say something stronger. But the simple proof of strong subjectivity does not hold the theory is not unitary, which seems reasonable. Yeah. Good.
Okay. One more question. Oh, you have one.
So you mentioned you have some special way of finding solutions that are not geodetic.
Yeah.
Does this apply for any SLM? Or
Yeah, that's any SLM with no issues, yeah. The trick is the connections are all flat. So they're locally equivalent to 0. So 0, I know how to solve the equation when the connection is 0. And so you gauge from there up to the solution you want. And people have been using this a lot in higher spin theory to find propagators and things like this, in fact. Yeah. So that trick doesn't care about the gauge group.
Okay, thanks Nabil again.